get into the. Well, that's good. Listen, you for practice, you can be calculus rowdies, right? I mean, so as things get exciting here, cheer if you want a little bit. That'll be fine. Okay, you can practice for tonight. All right. Do some chants, right? Okay, whatever. I believe. Okay, never mind. All right. So, here, all right. That might come in handy here in a little bit. So let's see what we got so far. So we got this definition of Riemann sum. And Riemann sum, if you just were going to sum up in just everyday language, would be what? R stands for? R stands for Riemann. R stands for rectangles. Riemann sum is just adding up, okay, sum, right? So we should get that word. Riemann sum is adding up rectangle areas. That's what it is. Now, it's easy to forget what we're, because we are going to get into the weeds here a little bit today. It's going to be some theory, a lot of notation, okay? It's pretty cool at the end what we end up with, but I apologize in advance. I think it's pretty cool, but again, some of it gets somewhat theoretical. But what we're doing is we're approximating the area under a curve. So what we're saying is, yeah, we know about antiderivative, we know about fundamental theorem part 2, but there are situations where we just can't do that. But so what we're going to do today is actually get the definition of a definite integral, the formal definition using limit. We talked about it a little bit yesterday, of what it means to do area under curve. Yeah, antiderivative lets us find it, but that only works when we can find the antiderivative, right? And so we're going to use this approximation technique to do and to explain what definition or what the definite integral is. All right, so the first piece of that is understanding a Riemann sum. A Riemann sum is simply adding up a bunch of rectangle areas underneath the curve. All right, now you can tell this is the height of the rectangle times the width, height times width, height times width, height times width, on and on and on for however many rectangles you add. You add that up, that gives you an area under the curve. Won't be the exact area, okay, unless you have how many rectangles? How many rectangles take for the exact area? An infinite number. We said 10 is not very good, 100 would be better, but you're not going to get the exact area unless you can do an infinite number of rectangles. And that's where we're going to head today. We're going to get to that, of what it would look like for having an infinite number and how that could give us the answer. Now, your homework is going to be made up of bits and pieces of kind of what we do. So as we go through the day, throughout the period today, I'll be pointing that out to you, and then I'll show you on the homework how it kind of all fits together. Okay? So there's a lot of notation that we have to work on along the way. So we're going to just do it as we need it, and you'll see how this all kind of builds on itself. All right? So the first thing I'd like to look at is this. This is just general notation for our approximations we've had so far. So you might want to jot these down. All right? So a left, just in general terms, because we want to be able to refer to these without having to do a picture every time, even though you guys drew some really great pictures, okay? But, it's not going to be necessary all the time. Now, in our next quiz, yeah, there's going to be some problems where you're going to draw. You're going to show me that you can draw some left rectangles, some midpoint rectangles, whatever. Okay, but there's also going to be some problems where you just give me an approximation where you don't have to draw a picture. Okay, so what do we need to know about a left? Now, n is the number of subdivisions, okay, number of subintervals. So we always start our left rectangle at the far left edge. We said that was x sub 0. And then we'll just assume we have equal widths all the time, so delta x. And then x sub 1 and delta x. And all the way to, not our last one, but one short of our last one. So x sub n minus 1, right, is the last one. Yes?
What would be the point of doing it with different widths?
I'm going to show you an example. The only reason you would do it with different widths is because that was all the information you have, like a table of values. Remember that one problem I showed you yesterday? If all you have is a table of values and they're different widths, that's what you got to do. But yeah, otherwise there'd be no point to do it. Okay, so that's a left. A right would look very similar, except with a right, we don't start at the far left edge. We go one width over, because in our first subinterval, we use the right edge, and we go up to the curve. So that'd be f of x1, and then delta x, and f of x2, delta x. And then we end at the far right edge, which is x sub n. Now, just notationally, right rectangles seem easier to work with than left rectangles. Just because you get to start at 1, end at n. You don't have to start at 0, end at n minus 1. But if we have enough of them, it doesn't matter if they're left or right. If we have an infinite number of them, it doesn't matter which one we use. So notationally, a lot of times we work with right rectangles just because the notation is a little easier to work with. All right, midpoint rectangles. Now, I went ahead and made this look like this. I just put M1 for midpoint 1 and M2 for midpoint 2, but we don't really work with midpoints if we don't have to, just because you have to figure out the midpoint all the time. Now, sometimes this formula is given this way, where they'll put, in place of the m's, they'll put this. They'll put x sub n minus 1 plus x sub n divided by 2, because that's how you find the midpoint. Is you have to take the left edge and the right edge, add them up, divide by 2. You know, so sometimes books will put that inside these parentheses, and then it really looks complicated. So I just put M1, M2, just understand you got to find your first midpoint, your next midpoint. So, okay, and then trapezoids. Excuse me. And the thing we want to know about trapezoids is that we start at the left edge, just like the picture we just drew. We start at the left edge, start at the right, use the left edge and the right edge, both. Add them up, times a half, times our width, delta x. And then we go x1 and x2. So x1 is the right edge of the first trapezoid, and it's the left edge of the second trapezoid. So it gets used twice. And all of the points get used twice, except the far left one and the far right one. They only get used once. So the x sub 0 and the x sub n only get used once. Okay, but anyway, so that's your basic trapezoid formula. So if you know these, and you had to do one of these sums, like on today's homework, you could do it without drawing any pictures, I think. Right? You could write it out and then calculate it as you needed to, if you knew what the function was. You wouldn't really have to have a picture of the rectangle or the trapezoid. Okay? All right. Well, at this point, what I would like to do is go back. Go ahead and have you pull out that 2012 free response packet, if you would find that real quick. And that's just a small little packet. Yeah, it says 2012 free response on the front of it. Looks like this. It says AP up in the top right corner. Okay. Does everybody have one? Okay. It was problem number 1, and we skipped part C, if you remember. Okay. And so what we had here was we had a table of temperatures of the water that was being heated. Now, part C says, for time 0 to 20, the average temperature is this integral right here. Now, we should know that. That's the average value formula. Now, we write it a little different than they did. They put this 1/20th out here. We need to recognize that, because the way we wrote our average value formula was from A to B, so 0 to 20, WT dt over 20 minus 0. That's how we wrote it. Okay? But that's the same thing, putting a 1/20th out front. So it's the average value of a function. So if we want the average water temperature, we would take the integral of the water temperature divided by 20. Well, you can't do the integral with the fundamental theorem part 2 because there's no formula, right? We don't have a function here that we can do the antiderivative of. So what we need to do is approximate with rectangles, okay? So right here it says use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate this. So to do the top part, we need to do a left Riemann sum. Well, a left Riemann sum is f of x sub 0 times delta x plus right? So what would I put in for this? So what is my first f of x sub 0? Wouldn't it be this right here? I mean, if you graph these points, and you could plot these points. We have 5 points. We're doing 4 subdivisions. The first left edge would be 0. You plug that in, you get 55. Go across, and then what would be the width?
Oh, wait, that one's 4.
Yeah, see what I mean? So this is that uneven width I was talking about. So first you'd be thinking, well, we're going 20. We're going to divide it into 4. That'd be 5 wide. Well, they're not all 5 wide. So we have to go by the widths that are here. So that's why it's important to think of that delta x every time. So this is going to be 55 times 4 plus 57.1, and you go ahead and write this down in your packet, then we'll have this problem done. 57.1 times the next one is 5y. But notice we're using the we're using the y value on the left edge of the interval. That's why it's a left Riemann sum. Plus 61.8 times 6, this one would be 6y, and then plus 67.9 times 5. And you don't use the 71, which is what we were just saying. With a left rectangle, you don't use the far right edge. So we don't use the 71. Now, some people might think, well, get the average temperature, just add these 5 and divide by 5, right? No. I mean, that would give you one approximation, I suppose, of the average temperature, right? This isn't going to be exact either, right? But this would be following this formula. So we go ahead and add those all up, multiply those and add them. And then we have to divide by 20, because what we're doing here is the top part. We're just doing the integral, right? We're adding up 4 rectangle areas, so that would be the area under this W curve if we knew what that looked like. So that would be this top. That's one of the biggest problems I think students sometimes have is when they do a left rectangle or a right rectangle Riemann sum, they forget that they're doing an integral, right? That's what you're doing, right? You're doing rectangle areas, right? So you're doing the area underneath. Okay, what do you get? 60.79. Which seems reasonable with that data. Seems reasonable that that would be the average temperature. Okay, but then it says, does this over or underestimate the average temperature? Why would this be under? There's the key. Since this graph is going up, if we plotted this graph, it would be going up. Left rectangles, and we're going to talk more about this in chapter 6. Left rectangles will be under approximation. But that's how you would explain your reason. You'd say that's an underestimate of the average temperature because the W function is increasing. Okay? All right, so there you get to see an example of using because the rest of today is a lot of theory that something, I mean, we're going to be doing some calculating, we're going to do some things, but here you can see kind of a problem that uses a Riemann sum, and you also get to see where these widths might not be equal widths. All right, good. Now, next thing, sigma notation. Remember this from last year? Vaguely? When do you use sigma notation? When you're adding stuff together. Well, think about what we're doing. We're talking about sums right now, right? We're talking about adding stuff together. So sigma notation is going to be handy. It's actually going to be a good thing. It's actually going to be very helpful to us. Okay? Sigma is a Greek letter S, so therefore sigma for sum. And so that's been the tradition, is to use sigma notation for sum. So before we get into this too deeply, we're going to do a little review of sigma notation. So see if I can find what I got here. All right. So here's a couple of examples. Let's do a couple of examples here of some sigma notation. Like, for example, this first one. Now let's look at the different parts of a sigma. You've got I equals 1 down here. This is called the index. That's why we use I a lot. And up here is where you finish. You always have to go by ones. You can't go by twos or something else. You can't go backwards. So it always has to start with this number down here, go up by ones until it ends with this number. And then the sigma says we do this that many times, and we add it together. So what would be the answer to this problem? Yeah, this is 3 plus 3 plus 3, 8 times. This would be 24. That's the simplest one you get. In other words, when i's a 1, this is 3. When i's a 2, this is 3. When i's a 3, this is 3. And it does that 8 times. Okay, now if you get this one, where there's an I right there, hard to see. Okay, I could make it a little bigger too. Okay, if you got this one where you've got this I right here, okay, well now when I is a 1, what's this? Well, it's I, but when I is a 1, that's 1. Then when I is a 2, then when I is a 3, right? And you keep going until I is a 6. So a lot of times on these problems, and the very first homework problems today are going to be this. They're going to be a sigma, just with a few of them to do, and you're going to expand this out. Now, if this was 1 to 100, then this would not be fun, right? But 1 to 6, we can just write them out and then add them up, okay? So for small numbers, we can just do that by hand, okay? But that's what a sigma is, and this is the formula here that generates the terms of our sum, okay? So I is a 1, then a 2, then a 3, then a 4, then a 5, then a 6. Add those up, get your answer. Okay, now there's a few down here. Let's just, look at a couple of others. Okay, like for example, number 6 here. Okay, so we would let I be a 1, we get 3. Let I be a 2, we get 8. Let I be a 3, 13. Let I be a 4, 18. Let I be a 5, 23. And then you would add those up. 11, 24, 34, 32, 65. Right? And there's your answer. All right. So that's sigma notation. Now, I doesn't have to start as a 1. Notice this one down here. It starts as a 2 and goes up to 8. Now, to be honest, we would rather do sigmas that start at 1. Okay, it makes it easier than 5. We know we should have 5 terms. On this one, you're actually going to have 7 terms because you go from 2 to 8. That's 7. Okay, so it's just a little confusing if you don't, but whatever, you can do that. You can start I wherever you want. Sometimes we use something other than I. I think you saw that one up here. We use J. This one up here, right here, they use J. I, J, and K are sometimes used. Okay, now what happens if we do want to do one where, okay, for example, this one, I equals 1 to 45. I don't really want to write that out 45 times and add that up. So it turns out for certain ones, there are some formulas we can use. Now, one of them, there's a story, there's an old story, and I don't know that it's true, but like many old stories, it's probably been exaggerated. But here's a couple of formulas. Why don't you write these down right now, and then I'll tell you this story. Call these your summation formulas. Now, on our next quiz, we are going to use these. I will give you these formulas on the quiz. Okay? And I think those are the only ones you need. I don't think you need the cubic. I don't think you need the cubic one. For the homework today. No, you don't. So just these 3. So we got sigma C, that's a constant. We got sigma I, and we got sigma I squared. Now, the n on top, so what this is saying is we can use these formulas, as long as I starts at 1, we can use these formulas for any number on top. We just plug that in for the n, and we'll get the sum. So this is going to work great if we have to add up 100 things or 1,000 things or something like that. We can use these formulas. Now, unfortunately, it works for I and I squared, so to get sine or something else in there, it's not going to work. But we're not going to do it with those, so we won't worry about it. All right? So, now the story goes, so the first one's like that first one we did where we got 24. We had a constant there of 3. So all this is a C plus C plus C plus C plus C n times. So that's C times n. So you have a constant. This would be like the one we did where we did 1 plus 2 plus 3 plus 4 plus 5 plus 6. Well, the story goes that there was a mathematician named Gauss who was a genius, and supposedly when he was in kindergarten, he was so smart that he was bored and he would cause trouble in class. So his teacher sent him to the corner and said, before he could come back to class, he had to add up the numbers from 1 to 100. figuring that this would keep him occupied for a while. And in like 10 seconds, he came back and he had the answer. How did you do it? And this was what he did. So, got the numbers from 1 to 100. This number plus this number, 101. This number plus this number plus this number, 101. Take the first number plus the last number, right? Multiply that by how many pairs of numbers are there. In this case, there were 50. So he just did 101 times 50 and got the answer. But in general, 100 would be the n. So how many pairs are there? If there's 100 terms, how many pairs? 50. So if there's n terms, n over 2. So in general, to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 out to whatever number, you just take n times n plus 1 and divide by 2, and you'll get it. So that's where that formula comes. Okay? If you have I squared, 1 plus 4 plus 9 plus 16 plus 25, if you're adding up perfect squares, then this formula will get it. So if you want to go from 1 to 100, 100 times 101 times 201 divided by 6, that's what they will add up to. So instead of adding up a whole bunch of those, so let's do a couple down here. Now, oh, by the way, and I skipped this, so let me go back to it here real quick. This is not surprising to you probably, but if you have a sigma and you have a constant inside the sigma, you can pull the constant out in front. If you're adding up things inside of a sigma, you can split it up into separate sigmas. So, that looks familiar. So, if you take just a couple of examples right here, if we take this example here, we could pull, if we wanted to do this problem right here, and you're going to have some of these on your homework, it's going to say use the summation formula to do this. So on this one, we could pull the 3 out in front. This would be sigma I equals 1 to 45. So we look up our formula. We got a 3 here. Our formula said what? N times n plus 1 over 2. So now you get your calculator out. You can multiply that. Do it real quick for me. 3 times 45 times 46. Divide by 2. Right? What is it? 3 times 1. Much faster than writing out 45 of those things and figuring it out, right? And if you had one like, oh, say this one down here, number 17, we could FOIL this first. We would have, we're not going to do this one, but we'd have 9i squared minus what? 30i plus 25. We could split that into 3 different sigmas and use those formulas, right? I could have sigma I squared. I've got that formula up there for it. N would be 38. So I would go 38 times 39 times, what was it? 2n plus 1, 77 times 9, right? And then 30 times sigma I, use a sigma I formula, with n being a 38. And this would be 25 times n, 25 times 38, right? So we could do this. So you'll have a little bit of this. That's going to come in handy for later for something we're going to do that involves integrals. So just reviewing some things about sigma notation, okay, and these formulas that we just wrote down. Did everybody get a chance to write those? Those 3? Okay. So we want to have those 3 formulas there. Okay. Written down, and there'll be some homework problems where you have to do that. All right. One last thing then with sigma. That we have to be able to do is if we have a sum, let's go in reverse. If we have a sum written out, be able to write it as a sigma. Why would we want to do that? Well, if you think about what we've been doing, we've got some sums written out. It would be nice to be able to write those in shorter version using a sigma. So, let's practice on a couple real quick ones here. If I gave you this sum and said I wanted you to write this as a sigma, the formula would be 3i. Does everybody see that? Now, maybe you don't. That was pretty quick. Okay? We would like I to start at 1. And it would go to 10 3 times 10 makes 30. When I is a 1, we get 3. When I is a 2, we get 6. When I is a 3, we get 9, so forth. That would be the signal. Now, I want to make a comment here, though. Yesterday, I told you I was making you write out those sums, and I said, I swear it's not for busy work because it's going to be about seeing patterns. This is what I was talking about. If I would have given you the, now you guys said it, Kelsey said it right away, but, or whoever said it, but maybe not everybody saw it right away. Okay? But I'll bet if I would have written this instead of this way, if I would have written this 3 times 1, 3 times 2, 3 times 3, right? 3 times 4, 3 times 10. If I would have written this and said, now find the pattern, doesn't that make it easier? So writing it out in a longer version, a more complicated version, actually makes this process easier. We can see the pattern easier because what we would do is we'd say, well, gee, every term has a 3 in it, so my formula is going to have a 3. And then the one that's changing, that's going to be the I. The term that changes is going to be the I. It goes 1, 2, 3 to 10. Oh, that's I. So 3 times I. So when you see that, it makes it easy. So now how about this one? Okay? So what if we had this one and we wanted to write the pattern? Not as easy, is it?
Is it 1.5 I starting
Okay. We had 2 things. Did you say something? Okay. We got 2 different ones going here. And it's possible there's more than one answer. Matter of fact, there can be infinite numbers of sigmas because you can always start at something different, right? But if you say, okay, Mitch, you said what? I plus a half. I don't think that would work because if I is a 1, you get.
We'd start at half.
You can't start a half. It's got to be a whole number. Okay, Kelsey, what'd you say? 1/2 I starting at 2. Whoops, I went into 3. We did it at 8. Let's check it. So when I is a 2, we'd have 1. When I is a 3, we'd have 1.5. When I is a 4, we'd have 2. Seems to be working. And then when I is an 8, we'd have 4. Okay? So that would work. Okay? But what if we wanted it to start at 1? Because they're just nicer when they start at 1 sometimes. But this would be fine. Now it would be 1/2 I plus, we'd have to make an adjustment, because if I is a 1, now we get 1/2 I, or we get 1/2, but we want it to be 1/2 bigger. It would always be too small by a half, so we would just add on a half. And then we could go to 7. So now, 7, you have 1/2 I, that's 3.5 plus half, that's 4. That would work too. Okay, now, if I would have done this though for you, if I would have rewritten this like this, right? Aren't these the same numbers? Now, I think it's easier. Because now we could look at this and we'd say, well, gee, every term has a 2 on the bottom. And then this goes from 2 to 8. So that would have been really easy to write that one, right? We could just put I on top, right? I goes, the top number is changing 2 to 8. Well, that's the same thing she told us earlier, right? Then what if I said, yeah, but I want to start that at 1. Okay, well, again, the bottom is 2 every time. And the top is what? Well, it's always 1 bigger than 1, right? So that'd be I plus 1. Now, isn't that the same as that right there? That's the same thing. That's I over 2 plus a half. Same thing. So that would be I would go from 1 to 7. But you see my point? My point is, the way we write them, sometimes a more complicated way of writing it, rather than reducing or simplifying, actually help us see the pattern better, writing a segment. That's going to come in handy for us down the road here too. Okay? All right. So those are the things we want to do with segment. All right. Now, might want to start a new page in your notes. We're going to go through a problem right here. Now, what we want to do, let me give you an overview because it's going to get easy to get lost in the weeds here a little bit. Matter of fact, why don't you stand up and take 60 seconds. I want you fully rested and recovered, ready to go for this. Yes, Bree, Kelsey, at any time, if you think this is overwhelming you, this is going to affect your play night, please take a break. You have my permission to do it. The rest of you just have to suck it up.
My killer voice and the rowdies.
No, that's why I'm having you sit quietly. Just listen. Just listen.
It's too dramatic. Speech.
Free routing.
Yeah, real quick. Good, you have 15 seconds. Try to stay awake.
Yeah,
God, it sounds good though.
it was really good.
Amazing what you do with an 88-minute lunch, right? Or 90-minute lunch or whatever.
Ooh, which one's the real palace? But Chinese food is staying awake, you know.
Yeah, I just have to eat it.
Yeah, we're both in the front. We're like trying not to fall asleep.
All right, here we go. All right.
Kelsey, she has to use her hand.
Is that bad? Oh, yeah. She's got that. All right. Here's a problem we're going to look at. So as you copy this down here, we're going to. Here's what we want to do. We want to write out. This is much like what you had to do today at the beginning. Just like what you had today, except we're not going to draw the pictures. Okay? So we want to take an area, which is this area here from 0 to pi. We're going to take this area, we're going to break it up into rectangles, and we want to work our way from what 4 rectangles would look like all the way to an infinite number of rectangles. We'll stick with rights. What would it look like for an infinite number of rectangles? Now, clearly we can't write out an infinite number of rectangles, so we're going to write it as a sigma notation. Okay, use a sigma notation to write that sum. And we're going to use those summation formulas we came up with, right? Those summation formulas to allow us to do those sums. Since there are going to be so many, we won't be able to add them all up. So we use those formulas. And we're going to show how an infinite number of rectangles is the exact area under the curve. So I had to pick one where we knew the exact area. Right? A lot of times we do approximation when we don't know the exact area, how to find the exact area. But I wanted to pick one where we did know it. So I went ahead and did fundamental theorem part 2, did the antiderivative, plugged in a pi, plugged in a 0, we got pi cubed over 3. Now somebody take your calculator and divide that out for me real quick. What's pi cubed divided by 3? Just so we have a feeling of what that area is there. I think it's 10 something. 10.335. I like how you guys automatically go to 3 decimals. Wonderful. All right, 10.335. So that's roughly our area, right? Under the curve. Exact. We know because fundamental theorem part 2 tells us that. All right. So let's start by doing 4 right rectangles. Okay, and we can, if we still need it, we can get the picture to help us here a little bit. 4 rectangles. We're going to divide this. It'll take 5 dots to do it. Okay, it'll take 5 dots to divide it up. What do we need to calculate first? To do our 4 right rectangles? We need the delta x, the width. What's the delta x going to be? Pi over 4, right? We're doing 4 subdivisions. We need 5 dots to do it, but it's 4 subdivisions. So it's going to be pi fourths, right, is going to be our delta x. So this first, now we're starting at 0, which makes that nice. So this first one is going to be pi fourths. What's the second one? No. 2 pi over 4. Why would we want to use 2 pi over 4 instead of pi halves? To leave 4 on the bottom and to see a pattern. Yes, good. So the next one will be 3 pi over 4, and the last one is going to be 4 pi over 4. Right? No, it's not pi. Well, it is, but 4 pi over 4. Okay? Yes, we want to see the pattern. Okay, so those are my points. Now, again, draw a picture. A lot of times I don't care what the function is, I wouldn't even draw the area, but I might at least draw the x-axis, put my 0, my pi, put some points in there, at least so I can kind of see what the widths are, so I can see that pattern. So sometimes I'll at least draw that part of it to help me see that. But you really don't even have to do that if you can see it okay. All right, so what is my first rectangle height? Use F notation. F notation. Forget the squared. This is f. F of pi over 4. We're going to use right rectangles. So my first right rectangle, I'm going to draw it, but you would never have to. I would come over here, and then I would go back to the right. That's my first right rectangle right there. So it's f of pi over 4. Now, the reason I don't want to do that squared, I want to stay with f notation, because if this function was x squared minus 3x plus 1, then putting a pi force into that would be a mess. It's just much easier to stay in f notation till the very end. Then we can plug whatever's inside here into our function then. Stay in f notation now is going to be much easier. All right, f of pi force times my width, pi force, plus f of 2 pi over 4 times pi force, plus f of 3 pi over 4 times pi force, plus f of 4 pi over 4, because I got to have 4 of them. I have 4 rectangles. We know we go all the way to the right edge when we do right rectangles. All right, so there are my 4 right rectangles. Now, that's a sum. I should be able to take that sum and write it as a sigma. Now, so instead of going to our calculator right now and trying to figure this out and add it up like you did on today's homework, we're going to write it as a sigma because your calculators have a sigma on it. And we're going to type in that sigma here in a minute. So let's write this as a sigma. So I is going to start at 1 and go to 4. That is right, because we got 4 things we're adding up. And we want to start it at 1. That's going to make it easier. So now we're going to look at everything that never changes in this sum. Well, the f never changes. The parentheses never change. You're getting ahead of me, though. Yes, okay, you guys are seeing it. You're doing great. You're way ahead of me. The pi force width never changes on the outside, so that's going to be there. The f, the parentheses, that never changed. The 4 on the bottom inside never changes. The pi never changes. It's just I pi over 4, isn't it? Because we got 1 pi, 2 pi, 3 pi, 4 pi. That's what I is. I is going 1, 2, 3, 4. So the formula is I pi over 4. So they're pretty easy to write. When you write this out, you're going to notice most of it stays the same. There's only one piece of it really changing. That's where the I goes. They're not very hard to write at all. Now, last thing before we put in our calculator is, yes, now we're going to go out of the F notation to our actual function. Well, what does it mean? German shorthand, right? Whatever's in here gets plugged in for the x. So even if this was a long, complicated function, we would just take whatever's here and we would put it in for the x. So this is going to be sigma I equals 1 to 4, and it's going to be I pi over 4 quantity squared, and then times pi over 4. And just leave it like that. Now you can go to your calculator. Now you can go to your calculator and type that in. Now I'm going to write it here, rewrite it. So that was I. It's in the same place your integral and your derivative is. Okay? Now while you're doing that, I'm going to do the hard work because I want Kelsey and Bree to rest here a little bit so they can just do that. I'll do the hard work here. All right, so what I'm going to do is I'm going to work this out by hand. So I got, okay, you're not going to have to do this except for one later we're going to do. I'm going to make you guys do it. But so I got I squared, and then this would be what? Pi cubed over 64. Now, isn't pi cubed over 64 a constant? So can I pull that out in front? Is that correct? And then that leaves me what? Sigma, oh, I squared. We had a formula for that, right? What was that? That was n times n plus 1 times 2n plus 1. Right? My n is 4, right? I think that's what it was, wasn't it? My n is 4 here, right? So that'd be n plus 1, 2n plus 1 over 6. And then that was times pi cubed over 64, right? So what is that?
5 pi squared over
No. What'd you get when you put the sigma in, by the way? 15 pi cubed over. What do you get when you do this? 4 goes into there 16 times. You guys are so lazy. 3 goes into here. 2. 5 times 3 is 15. Pi cubed. 2 times 16. 32. What's that as a decimal? 14. Does that make sense? It would be more. Right? Rectangles are going to be too much. 10.335, we got 14. But look how I could use those formulas. When I got to here, I could do this. That's a constant. Pull that out. I got my I squared. I could do my formula, and I could have found that answer. Okay, well, obviously that's a bad answer. That's 14. The answer is 10. That's horrible. Yes? Actually, left and right rectangles average is actually what trapezoid is. That's really what a trapezoid is the average of left and right. So if you think about the picture, we'll get that later. But yeah, here's a left, here's a right, and you average it. That's a trapezoid. So, but that's even more work than we need to do. That's even more work we need to do. Now, you're not going to have to go through this, and even on the homework, we won't calculate sigma like that. The one we do at the end, you will, and I'll show you what's going on there. But right now, this is more about the theory of it. This is not what you're going to have to do a lot of, okay, on the quiz, hardly at all. You're going to use the formulas a little bit. I might give you this problem right here, just give you this on the quiz, right? You're going to have the formulas at the top of the page on the quiz. I'll give you this, and so you might have to do some stuff, pull a constant out, plug in using the formulas, that kind of thing. But not in the context of a big whole problem like this, right? It's kind of like today's homework, just going to break it up into pieces. What's that? Like next Wednesday or so.
Is that going to be on the note calculator?
I think it's next Wednesday.
Yeah.
I'm not sure if this will be the calculator or not.
It'll go
After
on
the
third
end.
term though.
Oh, yeah. Yeah. All right.
Oh yeah.
So that's a lousy approximation, right? So what would be better? Infinite, but we're not there yet. 100 would be better. So let's do 100. Now, we're going to get a shortcut some of this because we're going to see patterns again. We're going to see patterns again. All right? So I'm going to draw my x-axis here real quick. You'll see what I mean by this. And so I'm going to have some subdivisions here. Now, I'm obviously not going to write 100 of them. But the first thing we calculate is what? Delta x, which would be pi over 100. Pi minus 0 over 100. My first edge here would be pi over 100. Now, if we were starting this integral instead of at 0 at 2, then it would be 2 plus pi over 100, right? That would complicate it a little bit, but we're starting at 0, so that makes it nice. What's the next one? Good job. Not pi over 50. We write 2 pi over 100, 3 pi over 100, 4 pi over 100. The last one? Pi. 100 pi over 100, right? That's the last one, which is, again, still pi. So, let's start writing these. My first rectangle height. No, use F notation. F of pi over 100, because that would be this up to the curve and then over, right? There's my first right rectangle. So it would be F pi over 100 times pi over 100 plus F of 2 pi of 100 times pi over 100, right? Height times width. Now, we're not going to write any more, But let's do the last one. 100 pi over 100. Now, if these were lefts, what would be the last one? 99 pi over 100, right? We would have started with F of 0. We just started at the left edge of 0, and we just stopped one width short of the far edge. It would have been 99 pi over 100. Would have been the last one. Okay? All right. Now, and while we're at it, what would a midpoint be? See, you can see why midpoints get a little tricky. What's the midpoint between 0 and pi over 100? Pi over 200. That's right. That's how you take half of something is you double the bottom number. You double the bottom number. Pi over 200 would be the midpoint. So you can see where that gets a little tricky. All right, now, but we won't worry about that till tomorrow's homework. After we talk about that some more tomorrow. But now you can see the pattern. It's very easy. It's easy to write this sigma. Okay, it's going to go from 1 to 100. We look at our thing we've written out. We've written enough of them out to see the pattern. Every one of them has an F in it, has parentheses, has 100 on the bottom. The width out here is all pi over 100. The only thing changing on top is 1 pi, 2 pi, 3 pi, which is I pi. We double check the last one just to make sure. If you put 100 in for I, sure enough, you get 100 pi over 100, which is what our last one is. That's why I always like to write the last one just to make sure that it fits. So that's nice. And then the last step here is to get it out of X notation, or excuse me, F notation. So we take our I pi over 100, plug it into the function, which was X squared. So this is what we're going to type into our calculator. So we got I equals 1 to 100. We got I pi over 100 squared times pi over 100. Now I can do the same thing I did when you guys were typing it in. I could go ahead and square that, pull out the pi cubed over 10,000 or whatever it would end up being, 100,000. And I can pull that all out and then do that formula again with 100 for the n. And I'm not going to mess with that. Go ahead and just type that in. And let's see what we get.
6,767 pi cubed.
That. Okay, give me a decimal. 10.491. Better.
Not good.
Still an over approximation, right? Still a little too big. Right rectangles should be a little too big for a function that's always increasing. Okay? Not good enough. We want infinite. How can we do infinite though? Can we put an infinite here? There is an infinity symbol on your calculator. It doesn't work, I don't think.
I'll try.
I think somebody tried it in the air class, said they got 0. Now, I didn't look at their calculator, so I don't know. That's what they said.
Where's the infinities?
It's where pi is. I think it's in that menu. So they tried doing their sigma and changing the 100 to an infinity. And where you run into trouble is this pi divided by infinity, I think. It's like, you know. So what do we have to do instead?
That'd be 0.
How-
It's pi over infinity.
Yeah, that's not the right answer, so we know that's not it. So how are we going to do infinite? We have to do a limit. We're going to have to do n rectangles, right? Not a certain number of rectangles. We're going to have to do n rectangles, and we're going to have to let n go to infinity. That's what we're going to have to do. So, last one. Last one to write out. Batiste, we've done 2 in a row, so this is going to be easy. Although it is going to have, instead of numbers in it like 4 and 100, it's going to have n. So we got to think about that. But our width, but the same process. So we do pi minus 0 over n, right? So our width is going to be pi over n. It sometimes causes people some grief at having that letter in there, but it's n rectangles, okay?
Just your final night.
All right, pi, free t-shirt, pi over n, okay? So pi over n, what would be the next one? 2 pi over n, right? All the way till the last one? N pi over n, right? That's the last one. So, this is going to be f of pi over n times pi over n plus f of 2 pi over n times pi over n plus dot dot dot. Oops, why am I doing an integral symbol? I meant to do an f. Okay, what's the same? So f of n pi over n times pi over n. I know we probably could have written the sigma, just change look at our last sigma, change the hundreds to n's, right? I mean, change the 4s to 100s is all we did last time. I get that. So let's go ahead and write it though. So we get I equals 1 to n, correct? There'll be an n on top. So this would be f is the same in all of them. The parentheses is the same in all of them. Pi over n is the same in all of them. We got n on the bottom. The top is 1 pi, 2 pi, 3 pi. So that's I pi. And again, 1, 2, 3. Finally, the last one, when I is an n, you put an n in place of the I, you get n pi over n, which is the last one there, pi. So, last step, take it out of the F notation. Now this one I am going to make us do all the way to the end instead of go to our calculator. Okay, I am going to have everybody work with me on this one. So I go out of my, so same thing we did with 4 rectangles, with 100 rectangles. Now with an infinite number of rectangles, we're going to take it out of the F notation, put it in there. Now we're going to work with that. So we're going to square that. That'd be I squared pi squared over n squared times pi over n. Is that correct? Everybody with me on that? I squared pi squared over n squared times pi over n. I'm going to go to a new page here. Okay, so what have I got? I got sigma I equals 1 to n. So I got I squared pi cubed over n cubed. Is that what I got? Now, isn't pi cubed over n cubed a constant? N is a constant. It's the number of rectangles. Now, I know we're letting that go to infinity, but it is a constant. I, though, is a variable. So we can pull out the pi cubed over n cubed. Oh, this is getting exciting. I know it's coming. All right, we end up with I squared. Look at that. Now, see, now I think you're just faking because I don't think it's that exciting yet. But okay, anyway. But you know what's coming. That's right. All right. Anticipate. And so the formula for I squared, we know is n. So, okay, so I got pi cubed over n cubed. And then the formula for I squared was n times n plus 1 times 2n plus 1, because we don't have numbers we can plug in there, right? Because it's actually n up here instead of 100 or 4 like we did earlier. All over 6. And we have to do the limit of that as n goes to infinity. Now listen, you're going to have some homework problems in it, and I'll show you when I pass that out, or when we look at it. You're going to have some homework problems that this is all they ask you to do. The homework today is going to be the bits and pieces of all this stuff we've been doing today. So you have some homework where all they ask you to do is this. They just give you this, and they ask you to do this limit, okay? So, but I want you to recognize as you're doing it, why you're doing it, where it came from. Now, how do we do limits as n goes to infinity? Well, you can't plug infinity. I mean, you kind of can.
L'Hopital's rule.
Well, but what you get is, listen, as n gets really big, you're going to get really big on top, really big on the bottom. Infinity over infinity. So L'Hopital's rule could work, but that's probably not the smartest one to use. High powers dominates better because when you multiply out this top, well, you not n cubed, not just n cubed. You'll get up here. You'll get 2n cubed plus a bunch of other lower powers that don't matter, so we don't have to worry about it, right? When I multiply this out, think about this because this will be on some lower problem. You'll have 2n cubed plus lower powers that won't matter. So you'll have 2n cubed pi cubed over this right here, right? What?
Figured it out. We're there.
2, the n cubes cancel, the 2, 6 reduce.
What?
Now some of you are sitting there going, pi cubed over 3, what do you mean pi cubed? Right there. Remember? Okay, now, yes, that is the exact area. Pi cubed over 3. How in the world, out of all of that mess, did that come out? That is, I think, amazing. Whew. Pi cubed. Okay, like I said, you're going to do bits and pieces of that. You're not going to have to do all that, but I did want you to go through that one time of seeing the integral. And I'll tell you a little bit about what we are going to have to do and where we will go from this. So, what we did, okay? Let's kind of summarize what just happened here, okay? All right. We said because it was over like an hour span, we wanted to find the area under this curve. We know fundamental theorem part 2 will work, but we also know that the area under the curve could be made up of an infinite number of rectangles. Rectangle areas is Riemann sums. So if we took an infinite Riemann sum, that should give us the exact area. So we wanted to actually show that, so we wrote out some rectangles. We wrote out 4, we wrote out 100, right? We wrote out an infinite. We used some nice sigma formulas and stuff like that to help us along the way, okay? But we just showed that an infinite number of rectangle areas actually gives us the exact area under the curve. So that is actually the formal definition. Just like limit as h approaches 0 of f of a plus h minus f of a over h is the derivative formula. I'm gonna show you here in a minute the definition of an integral. They're very similar. The derivative definition said we want the slope at one point. You don't know how to do slope at one point. You can't. You divide by 0. So we take 2 points and let them get infinitely close. That's what we did. Well, what we're doing here is saying, I want to find the area under this parabola. We don't know how to find that area. Well, let's take something we do know how to do, which is rectangles. Let's find that area, and then let's do an infinite number of it. So it's very, very similar strategies for both things we did. Here is the definition of a definite integral. Okay, so while you're writing that, a really good question for our next quiz could be explaining why this gives you the definite integral. Why does this sigma here on the right, why does that give you the exact area under the curve? And so I think an answer to that has to include all of those things in the red. Okay? What this is saying is that the area under a curve, f of x, from A to B, is calculating rectangle areas. F of c sub I is the rectangle height. Delta x of I is the rectangle width. When you multiply those two, you get area. So I think you need all of that discussion, that this is a height, this is a width. You multiply it, you get a rectangle area. The sigma does what? The sigma is adding them, in this case n of them. So the sigma is adding up the rectangle areas, and then the limit tells us how many. Infinite. We're going to add up an infinite number. So this is saying we're adding up an infinite number of rectangle areas, but that won't be a good enough answer. You can't just say that this is the definition because it adds up an infinite number of rectangle areas. Why is this rectangle areas? Because this is the height of the rectangle, this is the width of the rectangle. That needs to be a part of it. Okay? Now, here's the other cool thing from a notation standpoint. Look at the similarities between these two. Sigma is a Greek letter S. The integral notation. And it looks like an S. Sigma really is like a sum. Or excuse me, an integral is really like a sum. In other words, look at remember we talked about the dx and we said the dx is just kind of hanging out there and it doesn't really do anything. When we do the integer, it just disappears, but it really is there for a reason. Where's the dx come from over here? The delta x. The delta x. But now, we don't really have a width, and look at this, the function height, right? There's the f of x. I mean, they just look very similar. The delta x, think about the width. Now here, we're not really doing rectangles when we do the area, we're just doing the area. And we said this just kind of disappears. Well, think about it. If you have an infinite number of rectangles, how wide are they? Infinitely small. In other words, the width goes to 0. Actually, another way this is written is the limit as the widths go to 0, as all of the rectangle widths approach 0. Okay? Because that's what's happening. So all the rectangle, as you go to infinite number of rectangles, the delta x just kind of goes away. The width kind of goes away. So in an actual integral, the dx doesn't mean much. But so here's where I will use, though, the dx to help us in some problems. We did a problem the other day where this was gallons per hour, right? When we did the antiderivative, we said that answer gave us what? Gallons, right? Well, now, if we think of it this way, as rectangle areas, if we think of it as an infinite number of rectangle areas, what would the area of each of those rectangles be? Well, it would be the height. If you had the F graph was gallons per hour, the height would be gallons per hour. What would be the width? No. Just hours. The x's would be hours, right? Remember, because that's how we do a derivative graph. You had hours down here, gallons per hour up here. So gallons per hour would be the height. Hours would be the x. So the dx would be hours. So we could see that really what's going on is we would be adding up little rectangles that would represent gallons. They'd be gallons per hour times hours, which is gallons, and the integral then is adding them up. So we'll think of the integral, in some cases, we'll think of the integrals like a sigma, as like adding up an infinite number of rectangles. And it can help us in story problems come up with units. Now we already knew that if we do gallons per hour, do the antiderivative, that's gallons. It's just another way of seeing. Just another way of seeing. Okay, anyway, that's a lot. A lot today. So let's look at the homework. You've got this old packet, this LH packet here. This was, if you remember, if you want to go ahead and pull this out. This LH packet here was the packet where I told you to make sure you didn't do the first page, right? The assignment was actually on the second page. Well, now we're doing the first page. The first page, you'll recognize it's got a bunch of sigmas on it. Okay? All right. Now, and you guys will get a kick out of this, I'm sure. I noticed if you look at the assignment sheet, I did it again. So okay, so on the assignment sheet it says LH. It says LH 279. And it's 1 through 8. And then it says 9, 11, 13, 15, 17, and then 19 through 33 odd.
So it's 1 through 9 and 11 through 33.
Or it's 1 through 8 and 9 through 33 odd, however you want to do it. Okay? Yeah, it could be 1 through 9, whatever. Now, I want to walk through those. I want to walk through those sections with you. So when you do this, that's a different LH packet. You got the wrong one. There's two of them. We've had two different ones. Okay? I've got an extra one here, Mitch, if you need. Well, I've got one, I guess. One extra. No, I got one. Found it? Yeah, that's the one. All right. So on 1 through 8, 1 through 8, it says find the given sum. Well, notice they're all pretty small. 2 to 5, 1 to 4, whatever. So these you would just write out. So like I equals 1 to 5. So you put a 1 in there, you get 3. Put a 2 in there, you get 5. Put a 4 in there, whatever. So you go 1, 2, 3, 4, 5, write them out, add them up, just get the sum. Okay, so simple, just sigma stuff. You look at the next group. Now it looks like a big mess, but really this is what I was talking about. When it's messier, it's easier to write the sigma. So like on this first one, you got a 1. Everyone's got a 1 on top. Everyone's got a 3 on the bottom. What's changing? The number on the bottom, right? The parentheses. That's where the I would be. So this would, I would go from 1 to 9. It would be 1 over 3I, right? You see what I mean? So every one of these is like that. They look like a big mess, but they're actually, most of the terms will stay the same. You identify the part that's changing. That's where the I goes. And there you got it. Okay, the next group, 19, through this section, says use these sum formulas. So this is where you would pull out a 2, but there's 1 to 20, so we don't write all those out. So we use those formulas. Okay, like this one, you'd FOIL this, split it up, right? Use those formulas to come up with those sums. Okay, so we did that. All right, then you got the next group up here. It says find the limit as n goes to infinity. So remember I told you that? We had that one problem and I said, you just have this. So that's like high powers dominant, right? So these are just some high powers dominant. But you can see where these come from. That's why I really wanted to go through that today, so you recognize why in the world are we doing a problem like this. Well, you can see where it came from. It came from that sigma using the summation formula. Okay, and then the last two problems, 31 and 33, kind of have you do what we did right there at the very end. They've already got the sigma set up. They've got limit as n goes to infinity. All you have to do is kind of combine those last two sections we were just talking about. You're going to FOIL this out. The 1 over n cubed you can just pull out in front. You're going to FOIL that, split it apart, and then do the limit as n goes to infinity. Use your sum formulas. Right, now 31 is a little longer, 33 is a little easier. There's not as much to do on that one. Okay, so as you look at that homework, hopefully that makes sense. Every one of those is just kind of what we did as we were working our way through the stuff today. All right.
Bonus points if we go down.
Give.
Ooh, that's a great idea. That is a good idea.
That is a good, that's hard.
More people come.
We'll just
hard,
bring our
yeah.
shirt tomorrow and prove it.
Hmm.
Like it.
Wear your shirts tomorrow?
Wear the shirts.
No. Okay, so, good job, give yourselves a hand, way to pay attention and not fall asleep, appreciate that, even though you wanted to, I'm sure, many times. All right, rest of the time is yours. Whew, I can hardly talk.
I like that.
Okay,
You want to make a copy.
video. Video, yeah, cause you're pretty much gonna have to see that
Yeah,
probably
but
to know what we're doing. Okay. Yeah. You gonna do a gateway test? Okay.